In this video, we're going to start looking at some background topics to build us up ready to look at electrochemistry as designed for a general chemistry audience. However, when we start looking at electrochemistry, we're going to have to use gradients a little bit. And so it's prudent to look at some background topics early on. A warning, there's some math involved. The good news is the math is easy. I'll make it simple. The bad news for some of us is there's math that can produce serotonin, which can make people fall asleep, but best not fall asleep in the assessment. So hopefully this is for you, and we'll just look at some background as we gear up to electrochem. So the first thing we need to do is introduce the symbol del. So say hello to del. Del is a triangle with the point at the bottom, and del is a vector, and it's also a derivative in the three Cartesian axes. So del by definition is the partial change, or del of something is the partial change with respect to the x-axis plus the partial change in that variable with respect to the y-axis, plus the partial change in whatever variable with respect to the z-axis. Where we've got the three Cartesian axes, we'll say z is up top, we'll say y is that way, and x is that way. This d, this curly d here, is a partial derivative. It just means that we're looking at x and y and z independently. And we're not looking at, we're assuming that they're all independent, just like we can move independently in 3 dimensions in the Cartesian frame of reference. So for example, if I took del dot with a vector, let's say A, where A could just generalize a potential, then del dot A is dA dx plus dA dy plus dA dz. So here generally I've just said what del is, but we can dot del onto a vector. And once we dot del onto a vector, we return a scalar product. At this stage, I want to point out that we have del dot. So we're taking the dot product between del and this vector A. So we say del dot, and del dot is called the divergence. And as you can imagine from the word, divergence means something is being produced from a source. So for example, a geyser or a fire hydrant, if the head is knocked off a fire hydrant, water would diverge from the fire hydrant. It's a source of water, so that would be an analogous concept, and it will diverge in all 3 axes. So a spherical shell of divergence would emerge from that source. We're now going to compare, well, we're not going to compare yet, but we're going to add to our divergence the curl. So as the name curl suggests, it would be a curl or a rotation. If you were to put a test object in a system that has a curl, it would rotate. That would be evidence that a curl was present. And we're actually going to not only look at curl, well, first of all, we'll look at curl, I guess. So I'll say, whereas del dot A implies the divergence of A, del cross A implies the curl of A. So we call this the cross product. So this is del cross, whereas we had del dot for divergence. Now we have del cross. And here this product would give us another vector, whereas this product would give us a scalar. So we're now going to consider the fact, and it's definitely a useful fact, in electrochem, that the divergence of a curl is 0. So we're going to consider this statement here. It's going to help us moving forward, not only with electrochem, but it's a good solid notation to have at this stage, at this general chemistry stage, or at least in this general science stage, whether it be general chemistry or general physics for that matter. Okay, so let's look at the curl. So the curl is del cross, or the curl of A, vector A is del cross A. Let's put that in square parentheses so that we do that. And then let's take its divergence. So let's del dot it. So the curl is in square braces. The curl, the del cross. Now we take the divergence of the curl, del dot, and that equals 0. So we're going to prove this. It's useful. Anything that equals 0 is useful because then you can always transpose into the 0 and quantify something of choice. So we're going to clear up the board and we're going to prove that real quick, and it'll take us a few minutes. Okay, so we've cleared up the board. We do want to start to look at the proof that the divergence of a curl is 0. Before we do that, though, we have to learn how to execute the curl and then how to execute the divergence. Once we've done that, once we've looked at the general template, it becomes a piece of cake. But we do need a quick mathematical aside. So it's going to involve, these calculations will involve a 3x3 matrices, 3x3 matrix, and the calculation of its determinant, and a 2x2 matrix, and the calculation of its determinant. Recall from a previous video that the determinant of a matrix is the representative equation of that, it's the summary equation of that matrix. So let's have a look on how to do it for at least these 2x2 and 3x3 square matrices. So we're going to look at the determinant of a 2x2 matrix. This is the first thing we need to look at. So if we take a matrix, let's say A, B, C, D, and let's take the determinant, we'll put it in square, in parallel lines to represent, we need to take the determinant. Then we take diagonals, so A multiplied by D, and then we subtract the opposite diagonal, C multiplied by B. And that's as simple as that. So this is the canonical representation of that matrix. Again, for a square 2x2 matrix, so 2 columns, 2 rows. That's why it's 2x2. We take the diagonal elements and subtract them from each other. Okay, so that's straightforward. How about the determinant of a 3x3 matrix? So these are the only two types of determinant we'll need in electrochem, at least at this level and in these videos. So let's say we have a 3x3 matrix, A, B, C, D, E, F, G, H, J. I've missed G, H, well, on my notes I put G, H, K. I've definitely missed out I. It's quite common to miss out I because I can be used as a an imaginary, well, I is an imaginary number, so typically you don't label things I for that reason. J, I haven't labeled it J. I'm not sure why, but I'm going to be consistent with my notes. In case I upload these for my students, I don't want them unnecessary emails asking me why I've replaced J with K. Really, it doesn't matter. You just need 9 labels. So it really doesn't matter. You could call them Greek labels if you like, just so long as we can keep track of each label. Okay, so what we're going to do here is, first of all, we're going to look at this member of this column. So columns go vertically and rows go horizontally. We're going to look at the representative member of column 1, which is A, and we're going to multiply that by the following 2 by 2 matrix, which is this part here. So it's going to be E, F, H, K. So I need to take the determinant, using this procedure here, of this bottom right corner of the 3 by 3 matrix and multiply it by A. And then I'm going to subtract the following. And I'm going to go on to the next column now, column B. And now I'm going to take the outermost, so I'm still at the bottom, but the outer 2 members of column 1 and column 3. So I've got D and G, and I've got F and K. Take the determinant, multiply it by B. Now I'm going to add the third column, C, and I'm going to take the final 2 collection here. So again, it's this diagonal here with this 2 here. So D, G, E, and H. So D and G, E, and H. And again, take the determinant. So this type of thing is just something that you would memorize. Again, look at the pattern. I've got A, B, and C. I subtract A and B, but then I add C to it. And I've got 3 sets of 2 by 2 determinants, which I know how to do. For A, I've got the diagonal 2 by 2 down here. For B, I've got the extremities, so D and G and F and K. And then for C, I've got the other diagonal, which is D, E, G, and H. Okay, we'll clear up the board and we'll actually do, we'll clarify this by actually solving for the 2 by 2 determinants. Okay, so we've cleared up the board a little bit. I've restated what we had at the end of the last board. So now we just need to go ahead and actually execute the calculation for the 2 by 2 determinants in our expression. So this is going to equal, again, we look at the diagonals, EK minus HF. We scale that whole thing by A. Doesn't matter if you put the A here or here. We'll see why I'm choosing to put it on the right in a second. Minus, then we've got DK minus GF. Scale the whole thing by B. And then we're going to add DH minus GE. We'll scale the whole thing by C. Okay, so we've now solved our 3 by 3 determinant. And this will conclude the end of our aside. We're now ready to go ahead and prove that the divergence of a curl is 0, which will become useful in our electrochemistry. Okay, so we've tidied the board. I've restated what we had in the previous screen, which is our solution to a 3 by 3 matrix in terms of these Cartesian axes. So let's consider a potential A in a Cartesian field. So we've got the X degree of freedom, the Y degree of freedom, the Z degree of freedom. And I need to state my 3 by 3 matrix. So I'm going to state it and then I'll explain what the bits are, and hopefully it'll be self-explanatory. So I've got the three Cartesian axes, x, y, and z, but I'm going to make them vectors. I'm going to put a little roof on them, or a hat, whatever you want to call it. These are unit vectors, so x roof is a vector that points in the x-axis of magnitude 1 in whatever unit x is in. Y is a little unit vector that points in the y-axis of magnitude 1 in whatever unit y is in. Z, you won't be shocked to learn, is a little unit vector pointing in the z-axis, magnitude 1 in whatever unit z is in. So these are my unit vectors. Then I've got the divergence. So I'm going to take the divergence in the x-axis, d by dx, the divergence in the y, the divergence in the z. So remember we said earlier that del, our triangle, upside down triangle symbol, was d by dx plus d by dy plus d by dz. So they're my components of del. And then I've got my actual vector a. Well, a is a vector, so it has components in the x-axis, it has components in the y-axis, and it has components in the z-axis. So there's my matrix, and I'm going to take the determinant of this matrix. Okay, there's my template. Here's my solution. Here's my actual matrix. Now I've got to actually configure this to its absolute solution. So let this equal, I don't know, so I don't have to write this out over and over again. Let's call this, well, we can call this exactly what it is. It's going to be the curl of A, right? So if I take the determinant of this matrix, that's going to give me the curl of A. Okay? Curl. The curl of potential A. Okay, so let's actually use our template to execute this. Okay, so it equals, so I need EK, so if I look here, this is E and that's K. So it's going to be d by dy so E is d by dy, K is AZ, so that's EK minus HF, this is H and F, so it's d by dz, and then F, H and F, H is going to be AY, so AY. Put that in parentheses, and then I've got to multiply that by A, so A in this case is X roof. Then I've got to subtract from that the Y term. So I've got dk, so that's these two, d and k, which is those two. So it's d by dx, az hat, minus, then gf, right? gf, which is these two, which means it's these two, which is d by dz, and then ax. And then I've got b, which in this case is y roof. And then I've got to add my z term, which is dh. So fiddly, but there's nothing hard. We're just identifying numbers. It's more of a, can you identify this grid location here? That's all we're doing right now. With a little bit of patience, so we've got dh, so it's going to be these two, d by dx, ay, minus ge, which are these two, d by dy, ax, and I've got to multiply that by z roof. So I took my template, I took my actual matrix, I solved the matrix based on the template. So now I've got the curl of A. This is how I've taken the curl. Now I need to superimpose onto this the divergence. Remember, we're not saying that the curl of A is 0. We're saying that the divergence of the curl is 0. So let's go ahead and take the divergence. So recall, if I want to take the divergence, I've got to del dot this whole thing. So that means I've got to hit the x roof term with d by dx. I've got to hit the y roof term, which is this middle term, by d by dy. And I've got to hit the z roof term, which is this term, by d by dz. Okay, so I'm going to go ahead and do that in red so you can clearly see what's being added. So if I want to take, if I want to del dot now, I've got to hit this x roof term by d by dx. So d hits d and makes it d squared. And the dx just goes down here. So I added an extra d up top and a dx down here. Likewise, I add an extra d up top and a dx downstairs. Moving on to the next term. I've got to hit this whole term with d by dy. D hits the d and makes it d squared, and then I just add a dy down here. Likewise, d squared and dy down here. And then the final term, I've got to hit this with d by dz. D hits the d and makes it d squared, and then I've got dz, likewise d squared dz. Okay, so I've gone ahead and I took the divergence of this term. So now what I've got is I not only have the curl of A, but I went through in red and I took the divergence of that curl. So everything in red was the extra divergence term. Now I've got to show that this equals 0. Well, all I do, I just look at each term and I look for like terms or spectator terms. So I'm just going to go through and I'm going to cancel spectators. A spectator is anything that's the same on both sides. If you know anything about partial differential equations, and if you don't, I have another video on that's going to come out soon. Just a quick 20-30 minute video just on some basic partial differentials that you'll need in general chemistry, if you really want to understand it, that is. Then the order of these partial d's doesn't matter. So for example, partial dx dy is exactly the same as partial dy dx. That's not always the case with regular d's, but it's certainly the case with partial d's. Okay, so we accept that for now. Whether or not we understand it, we at least accept it. Let's see what we have. Okay, so I've got a d squared az, and it's positive. I'm looking for a d squared az and it's negative, so right here. So let's look at these two terms here. So I can get my shoulder out of the way. These two terms here. The numerator is identical, d squared az. This is positive, this is negative because of that negative sign. And then the denominators, dy dx, dx dy, they're the same because the order of partial derivatives is irrelevant. So these terms cancel, because positive one term minus the same term is 0. So we've cancelled those terms. Let's move on to the next term. I've got d squared ay and a z and an x downstairs, and it's negative. So compare this term with this term. I've got d squared ay and an x and a z in the denominator. Again, the order doesn't matter because they're partial derivatives. This whole term is negative, but I add an identical term, so it sums to 0. So that cancels with this. Okay, so far we've had 1 and 2 and 3 and 4. So we've seen 1 and 2 sum to 0. and we've had 3 and 4 sum to 0. So far so good. We've only got 2 terms left, so we don't even have to look. We've got d squared ax in both cases. And here we have z and y, the order doesn't matter. This says negative, but it's hit by that negative, so everything in this, well, that negative makes that term positive. But that positive term keeps that term negative, so I've got a positive value minus the same value which sums to 0. So let's call this 5 and 6. So these guys sum to 0. So I've just seen the proof that the divergence of this curl is equal to 0. And that's an important conclusion. So finally, in this video, we're going to show a similar proof using similar math, that the curl of a gradient is 0. So we know that del cross means the curl. We haven't seen del without a dot or a cross. So del dot is divergence, so the production from a source of a vector field. Del cross is the curl or the rotation of the vector field. But just del as another type of product, so not a dot product or a cross product, but just a good old product, is a gradient. So a gradient, you'll know by another name, it's just a slope. And forces act on slopes, etc. So we're going to rely on gradients, curls, and divergences a little bit in electrochem. So we're going to show this important conclusion that the curl of a gradient is 0. Okay, for our benefit, I've recapped the 3x3 matrix and its determinant that we used, exactly the same aside that we used in the previous slide where we showed that the divergence of a curl is 0. And I've also gone ahead and appropriated the correct 3x3 matrix that we need to take the determinant of. So we have our unit vectors in the x, y, and z axes respectively. We've got del, which is d by dx, d by dy, d by dz, as in the previous case. This time, rather than just have ax, ay, and az, we have d by dx, a, and d by dy, a, and d by dz, a. So we're going to go ahead and get going with that. And again, we're going to follow our template. So we're just going to follow it. We have EK minus HF. So EK minus HF. EK minus HF. So we've got d by dy. K is d a, so that's already squared a by dz minus hf, which is this one. So I've got d by dz, and then that's squared a by dy. And then I multiply that whole thing by a, which in this case is our x roof, the unit vector in x, minus our second term, dk, which is this one, which means it's this one, so it's d by dx, multiplied by d by dz a, so that's d squared a dz, minus gf. So gf is that, which means it's this term multiplied by that term. So it's going to be d a dx squared dz, multiply that by y roof, and then add finally dh, which is this one, which means it's that one. So d by dx, dA by dy, minus GE, which is this one, which means it's these two, which is dA squared. So GE is that one, so dx and dy, and multiply that by z roof. Okay, so I've just faithfully executed the template. Template's pretty easy to remember. And now the goal is to show that this is indeed 0. Okay. So let's go ahead and look at the first parenthetical term. The numerators are the same, so d squared a, and then remember the statement that for partial derivatives, the order doesn't matter, so y before z is the same as z before y. So if we look at that first term, that equals 0 multiplied by our unit vector x roof, minus, likewise, the numerators are the same, the denominators are the same. We've got a plus and a minus, so that's 0 y roof. And then we've got, again, two identical terms, opposite sign, 0 z roof. Well, remember what x, y, and z roof are. I guess I forgot to do that. Remember what x, y, and z roof are. X, y, and z roof are unit vectors in the direction of the axes of magnitude 1. So it's 0, 1, which is 0, minus 0 lots of 1, which is 0, plus 0 lots of 1, which is 0. So the whole thing just sums to 0. So again, we've just shown that this whole expression equals 0. We've proven that the curl of a gradient is 0. So just to wrap up this math heavy pre-overview of electrochemistry, so to preface us with some background ready to start using some of this terminology in electrochemistry, let's just summarize what we've come up with in the last half an hour or so. So the two big equations were that the divergence del dot of a curl del cross of some potential A is 0. And we had our canonical matrix that we solved the determinant for. We had the unit vectors x, y, z. And we should probably identify this. So these are the unit vectors x, y, and z. D by dx and d by dy and d by dz. This is del. And then we had our vector. Okay, so this matrix here, remember it only included this bit. We just del dotted it right at the end, so we didn't incorporate this del in our matrix. So hopefully you can see here that the del is three-dimensional. We have x, y, and z coordinates. We've got the del again, which is d by dx, d by dy, d by dz. We've got the vector itself, the potential in the x, y, and z axis. And then we always start with the unit vectors. Here we had the curl del cross of a gradient del vector, so there's no dot or cross, it's just a different type of product. The gradient just means the slope. And we know that the curl of the gradient is 0. And we had similarly a canonical matrix here. Now if you look at this matrix in comparison, again you've got the unit vectors. point in different directions in the Cartesian axes, magnitude 1 in whatever the unit of that axis is. We've got del again, but now we've got this thing here, which is del A, so it's del, but with A in it, so this thing is del A. So you can see the individual components. So here we've got everything included. Here we only had the thing in the square brackets included, and we just del dotted after the fact. So here we've got the unit vectors, we've got del this one, and then we've got del A that one. So this will summarize what we did in the last half hour or so, and this should stand us in good stead as we move forward with electrochemistry proper.